Well, good morning, ladies and gentlemen. A very warm welcome to you, and this is the opening talk of this year's Orkney Science Festival 2025. My name's Eric Walker, and it's my pleasure to be hosting this first talk here at the Picky. I'm really looking forward to the festival. I love all things scientific, arty, crafty, and I especially like the events which involve eating and drinking, although the organisers seem to have blotted me out of a few of those. Yeah. Now, before we begin, I've got to go over a bit of housekeeping. There are no planned fire drills today. The fire alarms are tested weekly, just to reassure you. This won't have any impact on this event, so if you hear a fire alarm, it is for real. The fire exits, there are 3 of them. There are 2 down here at the bottom, and there is 1 up the top. That's the door that you came in. So if you hear a fire alarm, make your way to one of those. Basically, if you're down here, just follow me because I'll be first out. The muster point will be out in the car park, and re-entry will be through the main building, which you came in earlier. Now, could you please check that your mobile phones are put into silent mode? Me and James have already checked, just to make sure that we don't embarrass ourselves. And just to prepare yourselves, we will have a roving mic at the end of the session. So please think about any questions you want to ask the speaker throughout the presentation. Right, our speaker this morning is Professor James Millen of King's College London. James has led the Levitated Nanophysics Group at King's College London since 2018, which explores the boundary between quantum and classical physics. And he uses the group's findings to develop real technology. Before this, James was a Marie Curie Fellow in Quantum Nanophysics at the University of Vienna. James is Director of King's Quantum, a research centre committed to the uptake of quantum technologies in healthcare for net zero and beyond. James today is going to tell us the story of how our understanding of the quantum world started 100 years ago, with Heisenberg completing the first step of that work on the island of Helgoland, and how the outcome of that work was the groundwork for the whole of modern physics. James, over to you.
And it's such a pleasure to be up here. It's absolutely beautiful waking up on a Sunday, being around, having a couple of dips, and you've got lovely clear water up here. And I'm going to try and go reasonably fast through this because it's the best bit of the questions, right? But this talk is going to be not really trying to teach you a lot about how quantum mechanics work, but where it kind of came from and some of the foundational ideas. So this talk, I should say, people sometimes get a bit confused. So I've written here quantum theory, and you hear quantum theory and quantum mechanics and quantum physics, and they're completely interchangeable terms. So if you really get the idea, you try and specify which one means. And so what is quantum theory? Well, as far as we know, it is the theory that describes absolutely everything in nature apart from gravity. And people think of it as something you just need to understand tiny things, and that's somewhat true, but we need to understand everything around the dark scale. If I wanted to, I could use quantum physics to describe a ball bouncing down the stairs, but that would be very inefficient. We've got other ways of doing that that are more efficient, but perfectly explicable using quantum mechanics. But there are some things which you need quantum mechanics to be able to understand, and there's no other way of understanding these things. So this is, your atoms, molecules, forces, how everything in nature sticks together. But we also need to understand, how to build materials. So, the way that solar panels work is the solar panels that you cannot explain how a solar panel works without quantum physics. There's no way of understanding this conversion of light to energy. And you can also understand some really interesting materials. So here's a superconductor, which can levitate above a magnet, and that's used, for example, in magnetically levitated trains. So that's kind of like what we use quantum theory for, but then of course, one of the things that people are very interested in is all this weird stuff in quantum mechanics, right? And so there are a couple of aspects of quantum mechanics, the way it describes the world, which is very different from what we're used to around it. And so one is called quantum superposition. And it kind of said, I mean, I've done a loose graphic here, which is, if I roll a dice and I get a 6, quantum mechanics would say that the likelihood of getting a 6 depends on all of the other outcomes I could have possibly got. So sometimes people use it, they butcher it, and they say quantum mechanics says that everything happens or anything can happen, and it's exactly the opposite. It actually kind of has really, really strict rules on what can happen, depending on what the possibility of things can happen. And this also extends to collections of objects. It doesn't just have to be one object, so you call this quantum entanglement, that even whole collections of objects, their behavior depends on all of the possible ways they could all behave together. So you get this interlink between lots and lots of different things at once in quantum mechanics. But I'm going to think more about that. I just wanted to give a place for what quantum physics is. But the really critical thing that sometimes missed out on is that it's not just a theory, it's something which already for more than 30 years people have been using field technologies all the time. So you always hear about quantum computers, this is and the next talk about quantum computing, so this is a superconducting quantum processor. Everyone thinks it would be fantastic, but quantum people don't actually do anything useful yet. There's already lots of useful quantum technology deployed, such as quantum enhanced communication, deployed by satellites or through financial centers or robots up inside countries, sending secure messaging. Or now you can even have quantum enhanced brain scanners, which you can wear and walk around with to do an MRI, but it's like, here's what happens. And the UK in particular has been very, very early at this technology and invested a lot of money. So back in 2013, they shocked the world actually by investing $1 billion into quantum technology. This was seen as a really bold move, and everyone's followed suit since then. And then as of a couple of years ago, they upped this investment to about $2.5 billion, and it looks like they're going to put more in actually now. Because of this, actually after the US, the UK has the largest private investment in quantum technology in the world, the largest in China, the largest in the whole EU put together. So the UK is really, really excellent in quantum technology. And there's real technology out there that people can buy. Maybe you can't buy it, I don't know how much money you have, but you can go to Toshiba and you can buy a quantum secure networking device that's 20 grand if you want to. Right. Good. That's my brief introduction. So I thought I should very briefly just telegraph a quick technical overview. So I'm an experimental scientist, and I'm really, really interested in why quantum mechanics seems strange to us. And one of the reasons I think is that it's not something we see at our scale very often. So the work in my lab was very much focused on trying to bring quantum mechanics to a larger and larger scale. And we work with the scale of nanotechnology, and we work with little nanoparticles which we levitate lately. So I really I've got some demo experiments here, so you can actually see stuff levitating, but getting this kid from London to Kirkwood defeated me in the end, I'm afraid. But this is where we imagine that we actually have reasonably close to a little silicon nanoparticle and make it rotate in every single direction at the same time, which would be proved quantum mechanics holds at that scale. And we'll talk about where quantum mechanics holds actually. And then we also like using levitating particles to build technology. So we build into devices because if they're sensitive enough to see quantum mechanics, they're sensitive enough to see all kinds of useful stuff in the world. And then really, really importantly, I don't know anything. I sit with my computer and I do talks like this and I write research grants. And these are the people in the lab who do this stuff. So this is my research team. And here are one of my labs as well. So lots of people doing interesting science. It's the best part of it. All right. Before talking about quantum mechanics, I think it's actually really useful to think about how we thought of the world before quantum mechanics came along in 1900, or really that time. So we split the world into two. One was what were particles, classical mechanics. And so in classical mechanics, you say that every object has a position and a velocity at every time. That's what classical mechanics says. Everything is a little thing whizzing around, and at any point in time, you know, its position and how fast it's going. If you knew the position and velocity of everything in the universe, you'd be able to predict what would happen all the time through the classical demon. But then we did also know there's a whole different type of object in nature, which is the field, which is something which is spread out over all of space. So this is, you can think of like electromagnetic waves or magnetic fields, or even to some extent sound waves. And they're spread out over all of space, and at every point in space, they have a size or a levelness, different sound wave, and a direction. Okay, and Maxwell's equations describe how they behave. So that's the two kind of things we have in nature. And actually, if you keep them in mind, I think that some of the ways that quantum mechanics behave is not so strange. And so from 1901, so quantum mechanics started in 1900. From 1901 to 1913, 6 Nobel Prizes were awarded for the study of various radiations. This was a high-tech period, it was all about radiation. The first being to röntgen for X-rays, and then from 1914 to 1917, all the Nobel Prizes were awarded for X-ray spectroscopy, so using X-rays to do things. And in 1918, we got the third Nobel Prize in quantum physics. So that was the high tech at the time. I think it's you can put your mind in the right place. All right, so let's get started. This is the reluctant father of quantum theory. This is Max Planck. I'll tell you a bit about him, because he's not necessarily that well known. So he was a professor at Berlin University between 1889 and 1937, and he was a scholar of thermodynamics, which, and he deeply admired Kirchhoff, who was his PhD advisor, and he studied the emission of radiation from hot objects for how things glow, and he termed this black body radiation, which we'll hear about. And also he was advised by Clausius, who understood how engines work. So Planck largely focused on the observation that radiation emitted from something, so when something is hot, is electromagnetic in nature, or in other words, light. So even before we get to quantum mechanics, Planck was studying the fact that when we get warm, it emits light. And that's what the warm do. So professionally, he was considered quite bright, although he was a clear and skilled lecturer. Some people describe him as conservative, impersonal, and stern, though others call him very high esteemed. And in particular, he had a very close relationship with Einstein. And they're very different characters. Planck was also a very skilled musician. He remained in Germany under the Nazi government, but he faced a lot of problems, such as openly opposed to the regime and supportive of Jewish people. In fact, his son, Erwin Planck, was executed for a failed assassination on Hitler. But back to the physics, in the 1890s, the German Standards Institute, located close to the University of Berlin, where Planck worked, was investigating whether electric lighting was more efficient than gas lighting. Because electric lighting was a new kid on the block, but no one really knew if it was going to be better than gas lighting in long term. Maybe it was going to take so much effort to generate electricity. Some people say that Planck was employed by this light bulb consortium, but that's not entirely clear. But he certainly seems to be inspired by the topic. And he started looking at it from like a theoretical point of view. How much energy does this hot object radiate? If I heat it up, that's how a light bulb works, you heat up this filament, how much energy will come out of it? And that's what we try to understand. So we always go back to this toy experiment called the black box. And it's a black box because we imagine that it perfectly absorbs the radiation. So you heat this box up, and all of the radiation stays inside, except for a little gap here where it can come out, so you can measure how much radiation is inside. So already from Maxwell's equations, we do that the energy inside this, which is electromagnetics, which is light, so wave, has the lowest wavelength, so long wavelength like this, where it goes from 0 up to a maximum, back down to 0 at the other end again. So we already knew that this was the longest, the most stretched out wave we could have in this box. But then you can keep on adding, this has stopped working. Then you can keep adding more and more shorter wavelengths to the light. Okay. Very old school. Then you keep on adding more and more shorter wavelengths to the light. So that's moving from red colours all the way up through to violet colours. You can just squeeze more and more shorter wavelengths of light into the box. And there's no limit. There's no limit to how short that wavelength can be. You can get as short as you like. So you have an infinite number of these beautiful modes, these short wavelength modes. And the problem is that in classical mechanics, and in fact this is true, there's a principle called equipartition, which says that none of these colours is special. So all of the energy in the box, which comes from heating up the box, all of the energy is shared equally among all of these colours of radiation. And so then when you try and work out how much energy would come out of this box, because there's more and more of these very, very short wavelengths, these high frequency radiation, you just squeeze more and more energy up into those short wavelengths. There's just more and more possible wavelengths. And you do your calculation, you find there's an infinite amount of energy inside, being radiated on this box. There's an infinite number of ways in which the energy can be contained within the box. And this is called the ultraviolet catastrophe. Really made the spectrum of this for quite some time. But Planck solved it. Spraying and punching that. So when we think about the energy of each of these different colours of light, what was believed at the time is that the energy of the light was related to how bright it was, or the energy of sound was related to how loud it is. That's not too surprising. So if I were to make my light, my wave bigger and bigger, which would mean my light gets brighter and brighter, then smoothly this energy just increases over time. And not every time, but if I can just smoothly increase the energy, much as I like, or as little as I like. But Planck said, you just don't what it is. What instead, this thing only have fixed energies, so fixed brightness, fixed loudness. What if I made this discrete? And so this means like that the light of a certain colour or frequency, so the light with one frequency, there's the lowest amount of energy it can have. The lowest amplitude it can have, and that here is related to the number of Planck's constant, which we'll come back to here. So the lowest energy that you can have. And this becomes important because now, if I'm sharing my energy equally among all of the different colours of light, but there's the smallest amount of energy allowed, then not all of the colours of light are going to get any energy. So we'll actually get to a point where you stop having these shorter and shorter wavelengths of light. So now you take this situation where you get an infinite amount of energy in your box, and it rolls over and closes down and you get a finite amount of energy. And this is true. So this is great because this graph on the right is actually crosses the experimental data and telescopes of the way that the universe glows. So that's the cosmic radiation, the cosmic background radiation. So the whole universe glows. It's a big black box. And you can measure that. And then the green line is what Planck predicted in the green curve. So this is absolutely sorted. And this way it's splitting the energy of the light into individual chunks. We call that mainly discrete or quantization. And that's where quantum comes from. That's where quantum theory comes from. So, Planck was awarded the Nobel Prize in 1918 for this work. And he was deeply worried about it. So he said, so it's a purely formal assumption. Actually, I didn't think too much about it. It was an active despair. He was just trying things out on paper until something worked, and this worked. but then he won the Nobel Prize, and after this point, his tone changed. He had to say, I was ready to sacrifice any of my previous predictions about physics for this. So once he got famous, he kind of didn't worry so much anymore. So the way that we noticed this sooner, it was, this bloke how anything that's hot glows. Why do you not notice it sooner? And the important thing is because the energy, the way it's split up, all depends on this number here, which you write with an H, which is called Planck's constant. And it isn't completely meaningless data, right? 6.63 times 10 to the minus 34 joules second. But that is like an unbelievably tiny number. So that means that the smallest energy that we can have is still really tiny. To give you a sense of scale, because the units here are energy times time. Typical energy scale of like just a day-to-day life, maybe 1 to 1,000 joules, and then time, again, a second is our normal time of experience. So we normally experience life in units of 1 on this scale. 34 orders of magnitude smaller, it's unbelievably tiny. But it is really important to say that even though it is very, very tiny, it still affects how huge amounts. So it describes how the whole sun glows. Right? So why the sun looks the favoured ultraviolet light instead is just nice and warm and orange. It is because there's a tiny little number that stops the energy being shown. So this completely changed the world, right? This is the beginning of quantum physics. Everyone's like, whoa, this is amazing. Not really. It didn't make a big splash straight away. Because really what it does is it predicts the energy with which something can radiate quantum individual chunks. So it's somehow quantized. And no one knows why or where it was coming from. So immediately people weren't that excited by it. Except one person who was very, very excited by it. And that was Einstein. So Einstein was one of the very few people who immediately saw that it was incredibly important. So I don't need to say much about Einstein. And he was one of the founding fathers of quantum theory, but also quite a vital character in his history, especially later on in his career. And his big motivation was, like, he really needed to have classical physics, which was little particles moving around. He had Maxwell equations, which is smooth wave. He didn't like that half of physics needs to be smooth. He interested in half with discrete and lumpy. And so he immediately, Einstein kind of saw, this is giving a wave is also lumpy. So it's very everything is lumpy. And he likes that idea. But he never managed to go with unifying cross physics. So a lot of the later ones created body involved with the currents and so forth. And he immediately saw why Planck's ideas were relevant to a really odd phenomenon that he noted not so long ago, about a decade before, which is called the photoelectric effect, which is whereby light actually knocks electrons out of metal. So I always, when I was learning this, I always read that it was like you shine light on material, sparks come out, and it's super exciting. And it's not like that at all. It's in fact really hard to find any kind of video of this happening. So I'm going to show you a video. It's not great. What we're going to see is that there's a drinks can, and it gets charged up. And you can tell this because there's also bits of foil hanging off it, and all bits of foil get charged in them, so they move away from each other. And then some of the parts here where the UV light and shine the UV light on it, and it knocks sort of the electrons out, and then they stop being repelling each other because they're not charged anymore. So here we go. And it's charging up things, bits of foil move away from each other, and then UV light, shine the UV light on the thing, and all the charges get knocked out. It's not that dramatic, but it was very mysterious to understand how it behaves. Because this is what you might kind of expect. So what you might expect is a situation where you have your light, which is shining onto the material, and if your light isn't very bright, and it's really dim, so you can imagine it's like a waterway where the peaks and the troughs are not very deep. And so in your boat's like the electrons, and they're just being bobbed around by this weak light which shines on the material. And if you shine a really bright light on, then you're really whipping the electrons around inside the material, so that the boat being completely thrashed around by these various things. So what you would expect if you increase the brightness of the light, then you absolutely wang the electrons out of the material, you wang the charge out of the material, but that's not what happens. What happens is you increase the brightness, you got more electrons, but it's still like really, really low, so it's still low energy, so it's still like very calm votes falling out of your metal, and how bright you made the UV light, you never got more energetic. But Einstein saw how he would solve the problem. And so some people say this is the most radical idea of 20th century physics. So what Einstein said was that energy during the propagation of a ray of light is not continuously distributed over steadily increasing spaces, but it consists of a finite number of energy quanta localized at points in space, moving around without dividing into capable of absorbed or generating only these entities. So he predicts that light was not like a wave. He predicted it was like a stream of bullets, which were called photons. The light came in chunks. And the energy of each photon, each chunk, he said the energy was related to its color, and then here it is, multiplied by the Planck's constant. So each little chunk of light has very, very small energy, but its energy depends on its color. And that was completely new. Everyone thought that the energy of light depends on the brightness, how bright it was. But Einstein found saying, no, it doesn't depend on how bright it is, it depends on its color. And if you have brighter light, you just have more of those higher energies, photons. So let's see how this explains the photoelectric effect. So here's my metal on the left, and so what I'm going to do is I'm going to send a beam of like low energy photons like this, and because they're like red at the low energy, then it can only knock the electrons out with a very, very low energy. But then if instead I make my light purple, which is a higher frequency, then I will knock out much higher energy electrons. They will come out much faster because each photon has more energy. And then if I turn up the brightness, they don't come out faster. They still one photon knocking out one electron. It doesn't matter how bright it is, the brightness can go faster, but it just means I can knock more electrons out. And that can't get the scratching our head out what is the photon. We're pretty sure light is a wave. It does one of those wavy things you expect. Things spread out in space, interacting, refracting, all of this. So these are the two different things that a photon could be. Right? It's either a wave, and here's how a wave behaves. So on the right, you have a beautiful image from Veronique Abbott of waterways, and there are two little vibrating bits that make these waterways, and you can see you get this lovely interference pattern as the waves overlap and cancel each other out and boost each other up. And the reason for that is that at this point here, where the light goes through, the light is spread out over this whole space, and the light comes out of both of these slits here and here, and it overlaps with each other and makes a beautiful pattern. So it's really important for the first situation there, so the wave has an amplitude everywhere in space, and so it has an amplitude in both those slits, and the wave downstream from the slit behaves that depends on that point. Or, as Einstein says, wave is like a particle, and then it's just like throwing lots of little bullets through these two holes, and that's entirely unsurprising. The behavior downstream has a collateral, dependent on the fact that there's a left slit and a right slit. If it goes to the right-hand side, it doesn't care that there's a slit on the left, whereas here, if I think about the wave coming out the right-hand side, by the time it gets back here, it's going to have overlaps with the wave with the left and right. And quite different situations and very, very easy to determine. So which one is light? So this is also another one of my video files. I like this one. So this is a video where you have a camera which can see individual photons of light. It's not so hard to do. You can see individual photons of light. There we go. So this screen is showing individual photons of light. So, okay, we've answered our question. Light is definitely a particle, because here we see individual photons of light just appearing like stars in the sky. just one photon at a time, a little bullet is hitting the end. So, okay, the thing you solve is clearly a particle acting like a bullet. But then the problem is, if you wait longer and longer and longer, and just keep waiting, you start to see where these little bullets of light are landing. They're no longer quite so random, and it forms these stripes. And those stripes are only things you expect from have a wave, because the stripes mean where you travel really depends on all of the places you could start with. So the photons look roughly at this screen like little particles, but the way that they travel seems to be like they got there and they were away. So you probably have maybe heard this if you've read the book of physics as wave-particle duality. This is a phrase I personally really hate. This photon is neither a wave or a particle, but certainly when it gets to the end of the screen, when you want to have a look at it, it arrives at a point in space. It certainly looks like a particle in Christ, but it's neither a wave nor a particle. So how would we work this? So I like to put a little bit of maths in our videos. You're always trying to avoid a bit of maths, but I really like putting this information up. Because quantum mechanics describes how things like this happen in a really simple, compact way, which is part of like, the philosophy of the whole theory, so I like to hear. So quantum mechanics always describes things with mathematical symbol, with the diagonal of wave function. And what the wave function is here is it's basically just telling you everything that your experiment can do. So, I don't know, I've got a box full of particles and all interacting with each other, and I somehow want to write down mathematically everything that can happen in this box. And so I give that to something more called you know. And quantum mechanics says that it is the sum, so that's the big black freedom here means the sum over all of the possible things that could have happened. So it's really easy the way quantum mechanics describes things. It says everything that happens, it depends on all of the possible things that could have happened. I remember I said earlier, that doesn't mean everything, because quantum mechanics puts really strict rules on what is allowed to happen and not. And this is not really a likelihood of come back to that. Or a likelihood, unavoidable. Yes, brilliant. This equation is actually kind of described as a constant superposition. All of the possibilities added up together. And it's the kind of thing that you know, we can use it very well, but it's the kind of thing that then people start to get very philosophical about, which I also like doing maybe later. So, you know, this is how people end up saying that there are like infinite universes or something, because each one of these possibilities is a different universe, and so what happens with these universes and stuff. But you don't have to live in your life. That's just you know. But this equation basically describes, you know, all of the properties of materials, semiconductors, superconductors, the periodic table, particle physics, and you'll hear more about that maybe this past while, I'm sure. So we heard that when we got to this point where I just said, even at that point, that was a bit later in quantum mechanics. We don't have a break because it's an avoidable one, and that's surprising me. And so I said that, you know, the photon, you know, sometimes it seems to travel or away, but it rises as the particle. And the photon's just like abstract little particle of light or something. But it turned out it's true for matter as well. And Louis Broglie won a Nobel Prize in 1929 noticing this, as a French prince. And you should see the paper he wrote. It's like, when we write a paper, you know, it's like, you know, 8, 10, 12 pages long with supplementary information and loads of references, and gets torn down by reviewers. He wrote like 2 paragraphs in one equation, no references, and he wins no Prize. But he predicted that this is true not just for things like light, but really for materials as well. And so, actually, this is slightly outdated now. So this is the largest object which is shown to have both these wave-like properties and the particle-like properties. So this is the largest object for which we know the quantum superposition principle holds. We've never needed quantum mechanics to describe the behavior of something larger than it. This is a molecule made about 8,000 atoms. The same research group has actually gone a bit larger now, but they're not stunningly larger. I actually worked with the team who are not on this experiment, and I asked them, what's this molecule called? So I want to talk about it. And they said, oh, if you don't want to know, it's like a business stand. So, but I'm not going to try. But what's brilliant is that molecules like this fluoresce, so you can see them. And so they were able to take a video up at the right of these molecules landing on a screen at the end of the fluorescence. And so you see they arrive in these individual red points, but if you wait over time, you see these brilliant molecules. So that's the double slit experiment, we call it, obviously very large molecules. And it does, use the kind of vitamins and plus a small plus of the metal around. So we know the quantum mechanics holds that you got that there. All right, so now let's talk a little bit more about the development of quantum theories, I guess, the Helgoland period further on. So really what we had up to this point was something like quantum 1.0 or the original quantum theory. And this is a whole series of observations which couldn't be explained, and then given in individual statements going, well, I think to the screen you can explain that, I think to the screen you can explain that. And so then people wanted to try and have a theory. And so they thought, well, if you've got this thing called a wave function, which looks a bit like a wave, then we know about waves in physics, so that's not a mystery to us. So surely if you write down an equation that tells me how the wave behaves. And so this is the wave function equation, often called Schrodinger equation. And it tells you how a wave moves. And I'm not going to try and explain it, but the important thing is it tells you how a wave changes over time, or how a wave function changes over time. And that means that now you can use quantum mechanics to make predictions about the future. So that was really important. There's loads of things that are very interesting about this equation. The first one is the total guess by Schrodinger in 1976. He didn't try to derive it in all kinds of ways he could, and so just fiddled around until he found something that worked. And still to this day, no one knows why this equation works, but it does. It's just a guess. It comes out of nowhere. This is also not sort of wave equation. It looks a bit like a wave equation. There's a couple of eagle-eyed scientists out there who look at the wave equation to be a second derivative and certainly wouldn't have the imagination over there. So that's a complex three-dimensional condition equation. So it's not even a wave equation. And this thing is certainly not a wave. It looks a bit like waves. You've got one particle. But at the moment you have a collection of particles, it's multi-dimensional, it's imaginary, it's got all kinds of weird properties. So it's not a wave, it's not a wave equation. This is why I'm hating with this very particle range stuff. However, Heisenberg, who I'm going to talk about, who I've got mentioned, he was very interested in it, and he had terrible allergies. Some tree pollen. So he went to Helgoland, which is an island off the north coast of Germany, where there's no trees. For a holiday to recuperate because he's been bored, so nothing to do there. So he just walks around a lot and he was like, he's like, oh, I don't know, I think this wave function stuff would make sense if it was really nice. It was like Greek numbers. He kind of wrote down the Greek numbers and it all made sense to him. And he thought, wow, I've discovered something new. And he went back to, I think he went to Bonn in Germany, and he was like talking about him, so the famous mathematician said, he's like, that's just a matrix. This is like undergraduate mathematics. We've not invented anything at all, kinds of terms. Anyway, Schrodinger won Nobel Prize in 1933 for this, so he wasn't that thrilled about it. And later in his career he said, I do not like it, I'm sorry I had anything to do with it. Don't even start talking about Schrodinger's plan. But what Heisenberg said, won the Nobel Prize actually before Schrodinger in 1932, is like, well, what is this thing then? And so Heisenberg said, well, it's a potentially infinite dimensional complex being vector in all of this place, right? So just like a load of jargon. But like, Fine. That's as far as like the whole school of thought went. It's just a mathematical tool. It's just a tool we use to describe the world. Stop trying to worry about what's wave function is. And it is good for making predictions because everything in quantum mechanics, everything is described by a wave function. So if you talk to cosmologists, they say the universe is described by a wave function. And what happened is Max Born came along, and he found a way of using this assumption. So Max Born said the wave function is a probability distribution, which is now a total guess. And still, we've never proved that it's true. It just seems to be true. We don't know why it's true. So Max Born, the German British scientist, and the living Newton-John's grandfather, and I found out just last week he is my academic great-great-great-great-great-grandfather, so my PhD supervisor, supervisor. That was really exciting to find out. Yeah. So he runs an Enterprise in 1954, by the way. So all he did is said, well, look, I don't really care what the wave function is, but I know how to use it. Imagine I'm looking at a particle in a box, and I want to go to quantum mechanics, and I want to write down the wave function saying, where is the particle? Undergraduate job, very easy to do. It looks a bit like this. This is what the wave function looks like. It looks like a photo on the 10, what I did. Actually, really interestingly, so what the Max Born said is that what you want to think about as wave function is like how likely it is to find with particles somewhere. So it's a maximum in the middle, and that means that it's the most likely to find the particle in the middle. And if I just like integrate, if I just take a slice out this, and I add it up, and then tell me how likely it is around to find it in this region. So now we can really use quantum mechanics and prediction is great. The probability thing. Already interesting actually classically, if you have a particle in a box, you're most likely to find it at the edges, but in quantum mechanics, you're most likely to find it in the middle. So really the point here is that the wave function is not this kind of thing, it's a description of what can happen. I mean, that's what we work with in quantum mechanics. We don't really work with the stuff of nature, we work with the description of nature, and we describe how nature is going to behave really well. And it's a philosophical approach to society, that's a problem of the world that's around nature. And it's really bad, actually. But this, is really, this was in the 1920s and we really come a long way. So superposition is a very common thing that we use all the time. So I particularly like this experiment where a team in the US where a single atom, and they put it in superposition of being two places simultaneously. That's very loose language, but we can use it. And those two places are separated by over 50 centimeters. So you can walk through this single atom. It's amazing. And entanglement, up to 10 trillion atoms being entangled together. And that kind of means that if you look at how many one of these atoms behave, it tells you something about all of them atoms, or change the behavior of all of the atoms. And entanglement you can use to communicate with the satellite galaxy, you can have things entangled over a day. So I just want to tell you that these, like superposition and entanglement, is not just like some abstract thing you think about, it's something that's used in technology and very robust. And you need both of these for quantum computing, which is our next talk. Just before I finish, I really like this thing which they're using superposition for. So if you get an atom and you put it in a superposition of here and here, then it becomes really sensitive to any changes in gravity, because if you happen down here, will feel gravity differently if the atom right here. New language again. And it is so sensitive now, we can buy devices that you can wheel over the ground and they can tell what's under the ground to no gravity. They can tell it like a pipe or a little trench or something or wires, just with the gravity. And so you can map from the ground with really useful statistical engineering. For example, I've seen videos of the doing these for a warehouse, and you can see all the boxes in the warehouse just by gravity. And that's very scary because you can't shield gravity. So you can see it, you can see the gravity, you can't have no shield you can put to stop you gravitation seeing something. All right, I'm going to finish up there. So that was just, I wanted to give you a flavour of where quantum mechanics comes from and what's realistic to do with it, whereas other talks throughout this People then will talk more in detail about the applications. And I'm just going to leave up on the screen when I'm finished. My institution being very funded, has done a fair bit of work up to here before, and unfortunately they've never had any events in Kirkwall, but they wanted me to say that they're doing an AI and computer science outreach event for young women, year 12 and 13. There's an online event, so I'll leave that slide up if you know what the interested might please share it. We're about to take any questions.
Right, well, we've got plenty of time for questions, and Elaine here has the roving mic, so if anyone wants to ask a question, just put your hand up, and we'll try and keep Elaine fit and healthy by running up and down the stairs. So if anyone has a question, just please put your hand up. I'll kick off, James. Sorry, there's one up there. We'll get that one there. Yes. My sort of first encounter of people conversing in quantum dialogue was at Heriot Watt. I was an undergraduate, and there was the physics lab there, and they were developing the first practical lasers and things like that. And these guys were talking in quantum languages, the best way I can describe it, which meant nothing to me at the time. So how were they? How were they envisaging? They were looking for applications for lasers, basically. They had the thing. They were then looking for applications for it. How would they use quantum science, quantum philosophy to do that?
Yeah, so actually, the mathematics of quantum physics is very, very simple. So now the things quantum computing is so popular and well pursued. It turned out it was relatively easy for even other fields to get into it, because actually the barrier to entry was quite low. Normally the challenging thing is always to have new ideas, and you don't have to. The philosophical applications don't really have much of an impact because you're trying to do something. You don't have to be worried about why quantum mechanics only predicts probabilities and not what happens if we still predict probabilities in real systems. And that's really useful as well. But in terms of working with light, if you use quantum mechanics to try to understand how to make one photon at a time, that's not trivial. You have one photon light at a time. And so a lot of development of the technology there has been special crystals, where you shine lasers in and it produces entangled pieces of light going out. So they actually can help you make these kind of quantum states sometimes as well. And that's used all the time in technology. So yeah, the data science and quantum mechanics go hand in hand. They enable us to make the things we should be able to work now.
Cool.
Another question.
Hello. You said at the beginning that you basically sorted it all out other than gravity, and then at the end you told us how you're usefully using gravity. So where are you putting your money on sorting out that problem?
Yeah, so it depends on what about gravity. So there's no issue in quantum mechanics with saying, I've got something that's being described by quantum mechanics, and I put it in the gravitational field, it's going to fall down or do something else. So there's no mystery there. But it's more of these, how you would describe the origin of gravity in a quantum mechanical way, that becomes extensible. So we can just take what we know about gravity and just add it to quantum mechanics and predict what will happen. That's fine. But we can't predict gravity from quantum mechanics. You can predict classical mechanics from quantum mechanics. You can predict Maxwell's equations. So it's like all most beautiful things you might do in an advanced undergraduate course is you can derive all of Maxwell's equations from some very, very simple at that level of quantum mechanics. So they talk to each other for sure. I mean, they're both aspects of nature. They're not incompatible in that sense, but we don't know how to formulate a theory of gravity from quantum mechanics. Is that clear? Okay.
In terms of the wave-particle duality, it's the case as the old view is a particle is a wave. You get a wave and a particle at the same time, and you got the Schrödinger box with a cat in it with an unknown release of poison. So it says that the cat can be both alive and dead at the same time. But very recently, they have observed a particle changing into a wave, or a wave changing into a particle. Does this mean that the cat is never both alive and dead at the same time?
Okay, that's two different questions, right? So the issue with having a wave particle duality is saying, well, a wave of what? I mean, no one's saying there's something that's waving. I tried to introduce it early on. What do they mean by a wave? Well, they mean something that's not like localized in space. There's something that's not like definitely here. Like we imagine little bearings rolling about, which are definitely fixed in a place, whereas quantum mechanics predicts that when things are moving about, it's not like that. They're kind of spread out over space. And there's like the size of this wave is like how likely it is that they're in any one of these places. Nonetheless, when you actually observe them, and it doesn't have to be a human observer necessarily, it can be if they're exchanging like energy of the environment, then you find them in a localized place. And that's the big mystery. Like how you go from this spread outness to being like definitely in one place. We call that the measurement problem, and that's the mystery of quantum mechanics. We really struggle with some of these terms. So the idea of going from this spread out thing to localize and spread out again, they're nice experiments, people do this, but there's no fundamental new knowledge, or it doesn't answer any philosophical question or anything. It's technical proficiency that people control the quantum mechanics that way. That's absolutely fine. Schrödinger's cat thing. Schrödinger, after saying it, immediately knew it was a ridiculous thing to say. He did a lot of ridiculous things as well, very terrible things. But he was making the point that, well, if I say that atoms can be in superposition, then, so the idea was that, well, how does nuclear decay work? Well, sometimes it's decayed, sometimes it's not, and that's random. Can I make it go up the chain? So if that's in a superposition, is like the detector that's detecting atom in superposition, and is the bio poison in superposition, and is the cat in superposition, right? And we perfectly well understand in quantum mechanics why that's not the case. It should be possible. Because the cat is not an individual quantum object. It interacts with the environment very, very strongly, and if you just write down quantum mechanics, and lots and lots of atoms all interact in their environment, then you don't have superposition anymore. So there is no Schrödinger cat. That's not within quantum mechanics, you can explicitly say, well, that's not possible in that kind of thought experiment. You'll see the term Schrödinger cat used quite often, but they mean something very technical, and then they mean something big in a superposition. And so that experiment showing the large molecules, you could say it was a Schrödinger cat state of a large molecule. That molecule's position was in more than one place at the same time. Also, as far as we're aware, for everything alive with it's not an immeasurable quantity in quantum mechanics.
Thanks very much for your excellent lecture. In Maxwell's time, I think there were competing theories. One was, say, if you had two positive charges repelling each other, then there was an idea of action at a distance, and the idea that things were embedded in the particles themselves. But then Faraday and Maxwell said, no, you've got to worry about the space in between, and the idea of a field emerged. And that also led to the idea that you can only communicate the information that one has moved by propagation of a wave through the field, which was limited to the speed of light in a vacuum. So is entanglement contradicting that and coming back to the idea of action at a distance.
Yeah, no, so Heisenberg certainly doesn't constitute that. There's no action at a distance. So this is the best way that I would know how to describe it. So the kind of thought of experiment we have is that you make a pair of entangled particles and they go whizzing off. And let's say they can either be thumbs up and thumbs down, or thumbs down and thumbs up. This is like an experiment thing you can do. There are thumbs, that doesn't matter. But you don't know which one you've made. And quantum mechanics says you've made both. They said you've made thumbs up, thumbs down, and thumbs down, thumbs up. They said these are the two, you made the both somehow. But then as you go and you measure one of them, you find it thumbs down, then, you know, sometimes popular say, well, it somehow tells the other particle it needs to be thumbs up. So it always looks the opposite, it tells the particle. So, but experimentally it's been shown that that happens faster than the speed of light. So it's faster than the speed of light communication. So quantum mechanics, again, very well understands that there's no information that's transferred faster than the speed of light. Entanglement is really useful for communication, but it's not because it's fast, because it's useful. So the way I think about it is, remember, quantum mechanics isn't describing little things whizzing around. It's describing these wave functions. And if I have this pair of objects, there's one wave function describing those objects. There's just one wave function. They may be separated out in space. Quantum mechanics doesn't really care about that. There's one description of this pair of objects. And so you say that you're measuring one of those objects. You're not. You're measuring the wave function. So even though you're measuring this one over here, you're measuring both of the objects. And that's non-local, because now you're measuring one object which is separated from space. It's non-local, but that doesn't mean anything traveling faster than the speed of light. I sometimes, you know, it's still not a great analogy, but I'd say it's more like popping a balloon. You know, they're spread over distance, and you make a change somewhere, it affects the whole balloon, right? It's one object, it all changes. And there's no information that you've gained in this situation. There's no way of proving, because to say that they've gained information, it would have to be that this was already thumbs up before you measured this one. If it's neither, then you haven't gained any information, not sent a message, you've just made the situation with a thumbs up and thumbs down.
Right, guys, there's quite a few people who've got potential questions for you. I'll explain to you how you can actually talk with James in just a minute, but I'm going to have to close this session now. We hope you're going to enjoy the festival, hope you are starting to enjoy the festival, and let other people know about it. If you follow us on Facebook and Instagram, you'll be able to keep up to speed with what's going on in the festival on a daily basis. Audience, can I just thank you all for your participation, and great talk. It really gets the mind working on a Thursday morning. So thank you very much, James.